I probably do a solver for I short circuit. For I short circuit. So let's write up these equations then. So if I look at this, I'm good right here, right? I'm good to about right here. So I'm going to write I short circuit here. So if I look at this here, I'm going to look at loop I. So if I look at loop I here, I'm going to look at this here. So I got one resistor. So I got 2I. And then I come around, I got minus 8. So I'm going to get minus 8, which is 8. And then I'm going to get minus, which is 6I. And look at that. I know what I is right away. So if I know what I is here, this immediately tells me here that if I bring this guy over, it looks like I must be negative 4. Right? Let's see, if I bring this over, yes, negative 2, sorry about that. So I immediately know I right from that loop right there. So if I know that current right here, the note, shoot, I don't even know, you see, look at me, I didn't even pay attention. Look at A right there. Look at node A. So if I look at node A, I'm going to say apply KCL. Can I apply KCL at that node?
Why would you do it there and not on the left?
No, I would not do that there. I would do it at this node right here. Let me call that node right there. Let me call that node A. So if I look at node A, look what I'm getting here. At node A, I'm getting what? I have I coming out, which is negative 2 amps. Obviously it's coming in. I got 4 coming in, and I now have I short circuit going like that. So you can see here that this current is really coming back in, so I get 2 plus 4 gives me I short circuit. So KCL tells me that this has to be 2 plus 4, which is 6 amps. So now, note that there's a very special situation here. Look at VOC, it's negative. Look at I short circuit, it's positive. So if I now come in here, and I'm going to say I want to determine RTH, you can see that RTH then is going to be negative 24 over 6 gives me negative 4 ohms. Let's go redraw this circuit. And this is what I said here, that there are very special situations for dependent sources in a Thevenin circuit, because you can get these negative resistor values. Now the question is, can I go to the store and buy a negative 4 ohm resistor? The answer is no, as you already know that. So I want to step back and look at this thing a little bit more. So if I look at the effect of circuit, it essentially implies that I could have this source, this circuit here, So if I look at this circuit here, this essentially says that I could come back in here now, and I'm going to put what? I'm going to put my load resistor in here. And what we saw here is that the load resistor was equal to 2 ohms, where I defined this to be the I. And so this circuit is effectively what? It's effectively this circuit right here. That was negative 4 ohms. And then I put my load back into here. And this load here is 2 ohms. Maybe not that in a minute. So what I want you to pay attention to this thing here is that if I look at this circuit and I now solve the circuit problem, you can see that these two resistors are in series here. And you got to treat that negative 4 ohm resistor serious. Okay? This is, remember, this is what? This is the effective resistance. Right? That's what we mean by that Thevenin resistance here. So if I now go calculate the current of the circuit here, so now I want to calculate the current of the 2 ohm resistor. What you're going to find here is that if I use just Ohm's law, tells me that this current of the 2 ohm resistor is then going to be what? It's going to be the voltage. If I look at the voltage here, it's got to be, the Thevenin voltage divided by what? The load plus RTH. And so as I start to plug in my numbers here, what you're seeing here is that this guy's going to be what? Negative 24 volts. That negative 24 volts guarantees that the current is going to be going what? Not from A to B, but you're going to see that it's got to be going up. Or is it? Because in this case here, the load is 2, and note that this is 4. So when I calculate this current, you can see here that this is giving me 24 divided by negative 2. The negatives cancel out, so therefore in this case here, I'm going to get what? 12 amps for the 2 ohm resistor. That means that even though there's a negative voltage source, the current is going down like this for the 2 ohm resistor. So far it seems pretty good, right? Because I'm just using Ohm's law, but then there's something very slippery with this negative 4 ohm resistor. So what I want to do now is that I want to step back here and I want to interpret of negative Thevenin resistance. Okay, I want to step back and I want to look at what is negative Thevenin resistance. Now, what I would like to do here is that I want to redraw the circuit again, but now I want to put a decade resistor box on it. So in other words, I have this circuit. And then here, I'm going to put a decade resistor box. So I end up putting here a decade resistor box. So that means I can change that value to any value that I want. Now, in some sense here, in a regular circuit, you would think that if I reduce the resistance in the series circuit to 0, that I'm going to get maximum current. So I would say that, sort of like if I was to make that, one assumes if R load, I should have called this R load still. So note that the R load is variable because I have a dedicated resistor box. That if R load is equal to 0, one should get max current. And that makes sense, right? If I have a series resistance, resistors add, if I was to set that resistor to 0, R load, you would think maximum current. Well, that is not the case when you have a negative Thevenin resistance. Because when I set R load equal to 0, then that means I still have this guy here. And I got a short right there, right? R load equals to 0. And when I calculate this current here, I still get a current that's going down like this for the load here. And you see here that this guy has to be what? In this scenario, you get minus 24, minus 4, so you get positive 6 amps. But you already saw that for 2 amps, for a 2 ohm resistor as the load, you can see that that's 12, but yet this is 6. So to sort of get a feel for where I'm trying to go here, right, you could imagine that I now take this resistor and I click it to 3 ohms. So now if I set R load to 3 ohms and I put it into the circuit, you can see that I'm going to get what? Minus 24, then I'm going to get minus 4 plus 3. All of a sudden, I'm at 24 amps. Oh, it's getting larger. And you can see that if I was to even set, if I now set R load to 3.5 amps, in this scenario here, I'm going to get 48 amps. And you can see that this is obviously getting larger and larger and larger. But if I now do what here? If I try to set R load equal to 4 amps, you can see that in the limit as R load of the current here, of the load, is then the limit as R load goes to 4 amps, you can see that this guy at minus 24, minus 4 plus R load, that this guy goes to what? Infinite. So in essence, if you could do this, you get max among power to the load. Right? That would be maximum. But note, there's no such thing as infinity. Right? It's a concept. So if you were to take this thing, and the maximum current that, let's say, the power supply can give would be, let's say, I don't know, 20 amps or something, then, in this case here, you would find that the maximum current that you would get then would be the 20 amp. It would reach the maximum of the power source here. So this kind of makes, this sort of like has a lot of hints as to how do you get this maximum thing here. And this is what they call impedance matching. And impedance matching is really nothing other than that you resonate the circuit. Okay? You resonate the circuit. And when you resonate the circuit, that means that you are maxing out the power that you can give to that one element. And again, what sets this thing? It's whatever the power supply. It's a power supply maximum. So you had a PLC that effectively does this. We already have the circuit, which is this circuit, and what you should try to do here is do the following thing. Look at the current, and just take this guy from 3.5, go to like 3.9, 3.98, 3.99, and you'll see that PSPI starts to give currents of the orders of, I think it's like hundreds of thousands of amps going through this thing. And then as soon as you get to 4, PSPI says, error, you can't do it. And it's because of this reasoning right here. And this impedance matching really has more power in AC circuits than DC circuits, but this is effectively a residue of that. Okay, so let's do the last circuit, and let's talk a little bit about maximum power. So the last thing that we want to do here is that if we want to talk about maximum power delivered to the load. So we talked about this, and if you go in and you read my lecture notes, you'll see that I gave a couple of paragraphs to talk more about impedance matching. So effectively, that's what that does here. And since, so we can write down any circuit into Thevenin form. So that means, regardless of how complicated the circuit is, we can always draw it like this. Right, where this guy here is the load. In this case, this will be Thevenin. So if I was to put some resistor load here, okay, so if you look at this resistor load here, we can easily calculate what that maximum power is here. Kind of worried about time a little bit. I want to make sure that I finish the circuit here. But what you would see here is that if I want maximum power, then you would have to then take the derivative of the load over D load, and then set that equal to 0, and then we've got to get the critical points. And so the way we did this in lab, I'll just highlight it very quickly, is that note that if this is a resistor load, I could use voltage divider rule to calculate the voltage across this one. And what we said here is that the power of the load would then be the load voltage squared divided by the resistance load. And so now if I take the derivative of this guy, actually, let me step back. I got to rewrite the load voltage. And so if I have a series circuit here, I could use voltage divider rule. And voltage divider rule says what? That the voltage across this guy is this resistor divided by the sum times that. So then I'm going to get R load over R load plus RTH times VTH squared divided by R load. And you can see that this whole thing is squared, so I could cancel out one load resistor with that one. So if I do this, what you'll see here is that I'm going to get R load divided by R load plus RTH. So I get that guy right there. So now all I got to take the derivative of that quantity right there. So then if I want maximum power to get that critical point, I then take the derivative of this guy. Now note, VTH is a constant, so I don't care about that. So I'm going to ignore that. I only look at that ratio right there. And the important thing here is that that's a positive sign, so I don't have to worry about the numerator, what happens down there. So when I look at this here, I'm really taking the derivative of R load over R load plus RTH squared. Now remember, like I said before, because this is equal to 0, I can factor out VTH. So here I go. So if I take the derivative of the top here, I'm going to get 1 times the top, the bottom. I probably have the order mixed up, and I don't care, because it's all equal to 0. So then if I take the derivative of the bottom, it's got to be twice this. And then the derivative of the inside is 1, and that has to be equal to 0. Note that there is a denominator, but that denominator is positive, so I don't care. So I just focus on the numerator. And one of the things that you see right away is that note that I have that bracket is the same as that bracket. So if I factor this out, right? So if I factor this out, that means I'm going to take this whole quantity and I'm going to multiply by 1 over R load plus RTH. Then you'll see that what I'm going to get at the end here is I'm going to get R load plus RTH. And then I'm going to get minus 2 times the load, which is equal to 0. And then you can see right away here that the critical point now is that R load must be RTH. So this means that maximum power occurs when this condition is met. So that being said, I could then go in and then take a circuit and calculate that. Which then brings me to the next example. Which is this guy. Now you may remember the circuit because we did this when we were playing with mesh here. So there's my load right there. So, no, I did not give you the directions. So that means you have to assume what is A and what is B. And for right now, so that we all get the same answer, I'm going to call this A and this B. And so this question's asking, what is the maximum power delivered to the load? Okay? So they want max power for the load. So how do I get that maximum power? Well, we already know that that load better be the Thevenin resistance. So then I got to go find that Thevenin resistance and then calculate that. Okay, let me give you some time to do that. Okay, I think this is a solid circuit right here. And you'll see that these things take a lot of time. So I'll give you about a few minutes, and then I think it's going to take me almost 20 minutes to do. So we'll have to move efficiently. And you can also see that I could take any circuit that you've done that looks familiar, and I could really change this thing, right? I could take IX, put it right here, and make that the load. Or I could make that the load, right? I could even make the power supply or a current source the load. There's a lot of little things I can do here. And it really changes the circuit a lot. Okay, let's look at this one here. So, what's the most efficient way for me to calculate this thing? There's a lot of ways to look at this thing here. Where would you put your ground? Huh? I think I'd put my ground right here. Because if I put my ground right here, then that means the node that I really want to solve for is this node right there, which is VOC. Now note, do I have the voltage right now? I didn't even think about that. Look at this. This guy's in series